Okay, we'll get started here. Thank you all for coming. My name is Patrick Hill, one of the founders here at Triple Point. Been working with Lagoon Systems for the last 17 years. Presented at dozens of conferences on all sorts of manner of things lagoons, and probably been on hundreds of lagoon sites at this point. So happy to share my knowledge and expertise with you here on this topic of lagoon phosphorus removal. So we are doing this Masterclass series, if you're not already aware, where we really wanted to create a comprehensive course, basically, that you could take on lagoons that would kind of take you from like the very basics all the way through to everything you would need to know to either engineer or operate a lagoon, or most of the things you need to know, I should say. And so right now we've done the first sort of 3 parts of this, and we're on our 4th part, which is nutrients. And so last week, my colleague Brady did a presentation on ammonia. I did a presentation on total nitrogen on Tuesday, and this is the last of our nutrient presentations on total phosphorus. Eventually, these will all be available to you on our Lagoon University site, which is an online free CEU platform, which you can go watch all these classes that we've given in the past and get continuing education credits for it, or PDHs for it if you're an engineer. So really great resource. We do this because we really want to help lagoons do it better, and I encourage you to check it out if you haven't already. So phosphorus removal in lagoons. Today we're going to talk about sort of an overview of the nutrients, some terminology, phosphorus limits, and then look at some ways in which you can kind of help manage your phosphorus if you do get a limit within your lagoon system, and all the different sort of pros and cons to different approaches. So within sort of like the nutrient world, these are all the main nutrients. I mean, carbon is obviously a big one. This is what our plants have been designed to treat in terms of BOD for many years. And BOD really is the basis of microbial energy. So all microbial sort of activity does sort of hinge on BOD to start. But other micronutrients are potassium, sulfur, and then micronutrients such as iron, magnesium, zinc, just these trace elements that we need. From a regulation standpoint, other than BOD, you're looking at phosphorus and nitrogen. And so, like I said, we talked about nitrogen earlier. That includes ammonia, nitrite, nitrate, and organic nitrogen. Today, we're going to talk about phosphorus. And the reason that these nutrients are important, and I'll touch a little bit more on it later, is that they have an impact on the downstream aquatic environment in which we are discharging our wastewater into. And so that's why there's such a heavy emphasis upon them on nitrogen and phosphorus in particular. So phosphorus is obviously on the elemental chart, or on the on the periodic table, and there's lots of different names for this, right? And some of this refers to a form of phosphorus, and some of this refers to just kind of a combination of several different forms, possibly in order to sort of categorize them, right? And so these are all the different forms. We're not going to talk about all of them. We're going to focus really on the ones that are specific to wastewater and specific to what we're trying to do here. But you've got total phosphorus, orthophosphate, polyphosphates, organic phosphorus, inorganic phosphorus. These are all just different ways to talk about phosphorus as a general category. So total phosphorus, primarily the main forms that we're focusing on for wastewater, we're focused on orthophosphate, polyphosphates, and organic phosphate. And some of these all these things together are ultimately what make up total phosphorus. So if you get a total phosphorus limit, they're going to test for, the test will include all of these things. Some of these are soluble, some of them are insoluble, some are reactive, and some are non-reactive. So when we look at what's coming into a wastewater plant, this is a typical breakdown of what's coming into the plant. We've got soluble reactive phosphorus, or ortho-P, right? Orthophosphorus, orthophosphate, and this is just one form. Then you've got soluble non-reactive, and that's usually a very small portion of your overall phosphorus coming into the plant. And the tricky part about this is that if you're trying to meet really, really low limits, you can't really do much about this soluble non-reactive. It's literally dissolved in the water. That's what we mean by soluble. So if we were to run it through a filter, right, no matter how small the micron of the filter is, it would seep right through, right? And it's non-reactive, so it doesn't react to chemicals. It doesn't react to a lot that's around it. And so it can pose a threat to not being able to meet extremely low limits. Then we have particulate phosphorus. So these are the phosphorus that bound up in the solids and the particulates coming into the lagoon. And then we have colloidal phosphorus, which is basically a hybrid. It's kind of like a transition phase between the particulate and the soluble phosphorus that's in your wastewater. This will become really important later on in the presentation, but I just want to break it down for you right here so you know. So phosphorus comes from several different sources when it comes into our plant. Human sources is big, or human excrement is a big one. Every living being, and I'll talk about this, is made somewhat up of phosphorus. It's a really crucial element to every living organism. And so we excrete this. We also get from industry or from recycling or household, cleaners or different things like that, or stormwater infiltration into the system itself. So this is just sort of typical breakdown of where phosphorus comes from that comes into your plant. So I wanted to spend just a quick minute talking about the different measurements of phosphorus, or just the different measurements in general. So we have obviously what's called parts per million, which is equivalent to milligrams per liter. And then we have parts per billion, which is micrograms per liter. And this can sometimes get confusing. And so when we talk about, let's say, for example, 0.5 milligrams per liter, that's half a part. And that's 500 micrograms per liter. Or people say ppm for parts per million, so 0.5 ppm, 0.5 milligrams per liter, they mean exactly the same thing. 500 micrograms per liter, 500 ppb, or parts per billion, same thing. It could be kind of confusing sometimes, and sometimes, a lot of times, we are talking about measurements that can be low, that can be in that parts per million or even parts per billion when we're talking about phosphorus. So like I said, phosphorus is essential to all living organisms, and we really actually need about 0.0 milligrams per liter, or 200 parts per billion of phosphorus in the water column, in our lakes and streams, in order to foster a healthy ecosystem, basically. It's also really important for our microbial communities within our wastewater treatment system. So if we don't have enough phosphorus, if we're phosphorus limited, then we can't grow the bugs that we need in order to break down the BOD, to break down the ammonia, or the other things that we want to happen. So a little bit of it is a good thing, ultimately. And phosphorus is used as a fertilizer. It actually fertilizes. It's one of the key ingredients in fertilizer to fertilize the growth of plants. And this is where you run into the issues with phosphorus, is that when it finds its way into our downstream environment, ultimately flowing into lakes and bays or ponds, for example. This is actually a picture of the Great Lakes, an area of the Great Lakes where they have had issues with what they call harmful algae blooms, or HABs, HABs. And these are primarily driven by phosphorus, but nitrogen is also a big component of what drives these. And they create a condition where you get this overgrowth of algae, right, which then kills everything else off, and then it dies and sinks down to the bottom and actually sucks all the oxygen out of the water. So that also kills all the different amphibious life within the water itself. So between this eutrophic, what we call eutrophic state, hypoxia state of low oxygen, and the harmful algal blooms, which are actually toxic if you drink water that has a harmful algal bloom. It's very, very bad for you. It'll kill animals. And the fact that 1/3 of all wastewater treatment facilities in the country or in North America are lagoon systems or have a lagoon system of some sort. That's 6,000 lagoons affecting all 50 states. We're really talking about something that's meaningful as an impact on the environment. So this is really the big reason why phosphorus can be regulated. So current state regulation is that your phosphorus limits really depend on a state by state and region by region basis, and particularly which watershed that you're in is what's happened, right? So the Great Lakes is a great example. Due to some of these harmful algal blooms, they've really worked hard to put regulations on all emitters of phosphorus that are upstream of the Great Lakes because it's such a wonderful freshwater source and wonderful habitat. Chesapeake Bay is another example of this. You see a lot of really stringent phosphorus limits around the Chesapeake Bay, but really any watershed where you're going into a lake or a stream where you want to make sure that it doesn't have the negative effects of eutrophication and harmful algal blooms. Limits are as low as 0.05 that can exist, like Wisconsin, for example, is fairly infamous for the amount of really low limits that it has on phosphorus, but other states can get that as well. I've seen very low limits, for example, in Ontario, in Canada as well, obviously with Lake Superior right there. But in general, I would say that most lagoons that I've seen are getting a phosphorus limit or going to get a phosphorus limit of 1 at least to start. And so the general sort of finger in the air, see which way the wind's blowing kind of regulation is you're going to get like a 10 total nitrogen and a 1 phosphorus at some point. That's kind of what I've heard across the board. So the challenges with phosphorus is you end up getting about 5 to 8 milligrams per liter coming into your plant. That's a typical municipal influent of phosphorus. Obviously, these permit levels are being lowered. In some cases, they're going to be really, really low. And treating to the really low levels can be expensive to implement and really increase operational complexity. The tricky part of it is unlike nitrogen, where we can denitrify and basically take the nitrogen and convert it to nitrogen gas and poof, it's gone. With phosphorus, we can't do that. There's no mechanism in which we can accomplish that. So ultimately, what we're trying to do in some way, shape, or form is to try and sequester the phosphorus within some kind of solid that could be removed and ultimately disposed of somewhere else. So how do we do this? I'm going to look at options for biological removal, which are few and far between for lagoons. We're going to look at alternatives like land application, constructed wetlands, and then we're also going to look at chemical precipitation, both in the lagoon and through a filter itself as a way to remove phosphorus. So land application, and I apologize for those who were on my previous webinar on Tuesday, but similar to total nitrogen, moving to a land application system is a way to essentially largely avoid a phosphorus limitation, with the caveat that sometimes there are limits on the amount of pounds per day of phosphorus and total nitrogen you can land apply within a certain acre. But largely speaking, to avoid compliance issues. When I started my career, I actually worked for a civil engineering firm that designed wastewater lagoon systems such as this one here in the picture, which is in Northern Illinois. And they designed them for basically subdivisions or developers that were trying to develop outside of a service area of a wastewater plant. And they would design an aerated lagoon followed by a storage and land application system. And in this case, they actually land applied on a golf course, but in other cases, they land applied on farm fields or other amenities or land that was around the wastewater plant itself. So I'm fairly familiar with the operation and design of these systems. I was there for about 5 years, so I learned a lot about it. Sat in a lot of board meetings and such. And like I said, it avoids compliance issues. It does minimize mechanical equipment. It reduces the need for fresh water on the irrigation land, and also reduces the need for fertilizer. Obviously, if we're taking the water that still has phosphorus in it, some nitrogen in it, or land applying it onto a growing crop, that growing crop is going to use that as fertilizer. The downsides are that it does require a lot of land. So you need land to store the water because you can't irrigate 365 days a year typically. And it also requires land to irrigate on. And so this is can be an issue. I'd say the desire to have land that's guaranteed for irrigation purposes is really important, because obviously if the landowner decides they don't want to accept your water anymore and you have nowhere to put it, that's going to be a big problem because there's only so much water you can store. So I would say that is another real concern is with this is like you either have to buy the land to guarantee that you can use it, or you have to have a very long-term agreement with the owner of the land in place such that you can use it and to irrigate your effluent out of your plant. It does require very careful monitoring. I'd say one of the issues with this too is I used to, not work with the operators, but I, be around the office as they were working on stuff, and there was always a concern at the end of the year: are we going to get rid of this water, right? Like we need to make sure that our storage lagoons are low enough such that if when we refill them over the winter months, right, we're not going to overflow them, right? And you can't irrigate every day, right? It's weather dependent, it's groundwater dependent, and things like that. So really different regulations, different places, but it can be a bit of a bit difficult to get rid of the water and stay on top of it and stay on top of the weather and be out there irrigating when you can irrigate and storing when you can't, right? So I'd say it's, from an operations standpoint, that alone creates a lot of complexity that I think certainly from a phosphorus standpoint, it's a lot easier to operate a phosphorus precipitation solution versus a land application solution in my experience. The other way to do this is to have constructed wetlands. So this facility here is down outside of Biloxi, Mississippi, still one of our largest installations to date for the company, 7 million gallons a day. They take their effluent from the primary lagoons, which are down here, and put it through the wetland lagoons, which are up here. And similar, to the land application system, you kind of you're running it through the constructed wetlands, and the constructed wetlands are removing the phosphorus prior to discharging, right, ultimately into the water body. So you're using them as an extension of your wastewater treatment facility. It can be effective. I've heard mixed reviews on the effectiveness. Some people have used constructed wetlands for years. Some people have used them, said they worked for like 5 years and then they stopped working. And so I think there's mixed there, but I think overall they're a thing. They're low energy, natural aesthetic, and fairly low maintenance. On the downside, again, you have this high land requirement. You can get seasonal performance variability. They're not going to work the same in the wintertime as they do in the summertime. Obviously, if plants are growing in them, they do require some maintenance, and they can be a mosquito haven in certain instances. So something worth looking at, but again, can have some questionable performance over time. So going back to that discussion about particulate and soluble phosphorus, and this is important as it relates to biological phosphorus removal. So, and chemical precipitation. So on the left here, you'll see that when your phosphorus comes into your lagoon system, approximately 80%, 70 to 80% of it is in the particulate form. And let's say the other 20 or 30% is in your soluble and reactive form. So we talk about reactive in terms of this is what we could actually do something with, or what's easier for us to do something with, particularly when it comes to reactive in terms of what a chemical will actually bind to. It'll more readily bind to the reactive phosphorus than the particulate phosphorus. As it moves through your plant, a lot of that particulate, most of it, the vast majority of the particulate phosphorus actually solubilizes into the reactive form. And then at that point, that's where either it's bio-P or it's chemical P, you're looking to basically convert that back into the particulate form from the soluble form, and then ultimately settle out those solids and dispose of them. So I think that's important to note that, you know, when you look at a mechanical plant solution, is that you're not removing the phosphorus in the sense that, like you are, let's say, with BOD that turns into carbon dioxide, or total nitrogen that turns into nitrogen gas, right? All you're doing is sequestering the phosphorus in the solids that then gets removed at that point. And so that's what a mechanical plant will do. And you can do that biologically. That's what a mechanical plant will do biologically, or you can do it from a chemical standpoint. And a lot of times mechanical plants do it from a chemical standpoint, but you can certainly do it from a biological standpoint, or both at the same time. So the downside of a mechanical plant is that you do get these high capital costs associated with, sometimes it's 3 or 4 times the cost of upgrading a lagoon system. Certainly if you're comparing it to chemical precipitation in lagoons, it's probably like 100 times more expensive, because chemical precipitation, equipment-wise, is fairly low cost. It does increase operational complexity, requires more staff, requires a higher operator license, and in a lot of cases, just not a great option. So I'd say overall, like this would not be my first choice, and I don't think this would pan out in any way, shape, or form when it comes to removing phosphorus from a lagoon versus, let's say, doing a chemical precipitation approach to it. So lagoons. So biological removal in lagoons is not really a thing, and it's not something that's been proven. I don't think it's even something that's been really attempted. Not entirely sure why. I'm not an expert on bio-P, so to be perfectly honest. But what you do see across a lagoon is you do see some natural assimilation and uptake of phosphorus. Like I mentioned before, phosphorus is required in order to grow the microorganisms that treat BOD, the nitrifiers that treat the ammonia, etc., the denitrifiers, which are similar to the BOD consuming bacteria. So that you do get that assimilation of the phosphorus into their cell walls as they grow. So that removes some phosphorus, and then ultimately they die and sink down to the bottom, and that gets sequestered. That phosphorus then gets sequestered in your sludge. The other ways is you get algae and duckweed that grows that will also assimilate the phosphorus into its cell wall and die and sink down to the bottom eventually. However, algae will also just flow out of the effluent of the plant, right? In some cases, duckweed as well. But so it goes that way. The problem, of course, is that when that algae flows out of your plant, you take your sample, take it to a lab, the phosphorus that's in that algae ultimately shows up as total phosphorus in your sample. So not necessarily ideal, but this is what happens. If they do grow and then die and sink down to the bottom, you get that natural sequestration or that natural settling of phosphorus at the bottom, which is really great. And then eventually, from a normal standpoint, you remove the solids have some phosphorus in it, and you could potentially land apply those. So when you do chemical precipitation, what you're looking to do is you're putting a precipitant in the lagoon that's essentially binding to the phosphorus molecule along with other solids, right? It's somewhat indiscriminate in terms of the way it binds to things. It'll bind to the phosphorus, it'll bind to the suspended solids, and then it settles those solids down, right? So that's one thing. And typically what we've seen is you can get down to less than 1 milligram per liter, and I'll show you some case studies, just by feeding chemical into a lagoon and ultimately letting those solids and that phosphorus will bind up with those solids settle. And then the other thing you can do is you feed the chemical to bind, creates a larger solid with the phosphorus molecule, and then you send that through a filter, which we'll talk about, which ultimately is a physical barrier. Clean water goes through the filter. Phosphorus and solids stay on one side. you get down to 0.1, potentially much lower than 0.1. So, the idea of precipitating phosphorus and letting it settle is definitely not new to lagoons and not new to wastewater treatment. This has been done in mechanical plants and clarifiers for decades, and has been very, very proven to be effective. For lagoons, it's also been used for decades. We've been doing work in Michigan, for example. Michigan has a phosphorus limit of 1 on lagoons. It's had a phosphorus limit of 1 on lagoons, so ever since I've been working on lagoons, so 17 years plus, and regularly meet a 1 milligram per liter phosphorus limit there without too many problems. The extent to which you can get either ferric or alum, these are typically the chemicals you use to bind the phosphorus and ultimately settle it out, is dependent on the extent to which you can mix those chemicals and get the chemical and the phosphorus together, right? So mixing is really key. And you can very easily, the issue with lagoons versus a clarifier is you can very easily overdose chemicals in lagoons, and ultimately the more chemicals you dose, the more solids you build up on the bottom. So there are two main types of chemicals that are used. You got aluminum salts and iron salts. So alum and ferric, that's what you hear. And then you've got these different forms of these things. So you have aluminosulfate, sodium aluminate, polyaluminum chloride, right? Ferric chloride, ferrous chloride, and ferrous sulfate. And I'd say there's a pros and cons on the slide. I'm not going to go through the pros and cons of each, but in general, the sort of beef that people have with aluminum salts is that they tend to create a more thicker and sort of concretized sludge, right? And the beef with ferric is that it's more acidic, it's more corrosive, it's harder to deal with, right? And so people have their different preferences in regards to the handling of it and or the result of it. But ultimately, what we recommend and what you should definitely do if you're going to look at doing this is you want to start by doing jar testing. And that's where you work with a chemical supplier to get a sample of the water, right? You get a sample of water at some point, either at multiple points in your lagoon system, so influent, lagoon 2, cell 3, etc. And then you also want to sample and test using different chemicals, right? One of the 4 that I mentioned or some other one, to see what works best, right? To see what can get the chemical, get the phosphorus levels down to your target requirement, to see, cost, things like this, how much you have to dose in order to achieve that target, because everybody's wastewater is a little bit different. And so these chemicals, I don't think that there's an easy way to pinpoint one chemical for each application. You really need to do this jar testing to ensure that that you get the right chemical. So once you kind of figure out the chemical, you want to look at feed point. And this is a really critical decision. So typically what I see is that people feed, at the influent location, between 2 lagoons, or potentially directly into the lagoon itself. So we've actually pioneered this concept of actually feeding it through our aeration and mixing unit, the Aries unit, and that obviously you have a little chem feed line with an injector coil, goes in the stack tube, and you feed it and it goes up, right? And so this kind of makes it so you can feed it really anywhere in the lagoon you want. But this really matters. I think that there are several factors that can play in here. There can be, where do you have power? Where can you store it, the chemical, right? You have to have a chemical sitting there being stored, right? What your lagoon design is. Maybe you have one big lagoon with 3 baffles, right? You don't have a transfer structure to feed the chemical into, right? So that's going to affect where you feed it. And ultimately, where you feed it's going to determine how much phosphorus you can remove, how many solids you're going to accumulate removing that phosphorus, et cetera. So really critical decision. I'd say, overall, we've looked at this a decent amount, and there's one 3-year study that I'll cite here where they looked at, okay, I'm going to feed at the beginning of the lagoon, I'm going to feed at the back of the lagoon system, more in a polishing pond type of setting, and they found that they were able to reduce 60% at the front and 81% at the back. So they got more effective phosphorus precipitation at the back of the lagoon system than at the front. So this kind of makes sense, right? Because what happens is if you feed at the beginning, the chemical reacts with the phosphorus, but it also reacts with all the non-phosphorus things that are present right there at the beginning of the lagoon system. So that's your BOD, for example, and all the other solids that you have coming into the system at that point, right? Your BOD, your TSS is higher at the front of the lagoon than it is at the back of your lagoon system, right? So you see that, and what that causes you to do is it interferes with the chemical reaction that you want to precipitate the phosphorus, but it also requires you to use more chemical, right? Which is obviously not such a great thing. The second part of that is that if you feed too much chemical, it can actually interfere with the BOD reduction, so that could be of concern. You also, if you feed chemical at the front, you're going to settle more solids because you have more solids there, which is going to speed up the rate at which, right, you're accumulating sludge on the bottom, and ultimately speed up the rate at which you're going to have to remove those solids. And the third thing is that, as we talked about earlier, when we have the phosphorus coming in, most of that phosphorus coming into your plant is in the particulate form and is not as reactive to the chemical. It's only once you get further down in the process where you have the more soluble phosphorus that's going to be more readily reactive with the chemical, and it's going to more readily bind to the chemical itself. So all of this, I think, pushes to feeding closer to the back, right, of your system, and that being a much, much better approach than feeding at the beginning of the system for all these reasons. Ultimately, I think if you're trying to meet a really low limit, you might have to have multiple injection sites and possibly a filter, which we'll talk about later, but these are some of the considerations on location. Now, not so fast, you say. What about algae? Well, algae is a concern, and what happens with algae, as we talked about previously, is the algae will actually assimilate the phosphorus into its cell wall. And when it does that, it makes it much harder to precipitate because the chemical and the phosphorus don't react very well together, right? And then further downstream, if you have to put a filter in to meet a really low phosphorus limit, the phosphorus will actually squirt through the filter. It'll squeeze through the 10 micron or 5 micron filter in a lot of cases. And ultimately the algae gets tested, the phosphorus, and the algae turns up in the phosphorus in your test result. So a big issue. So I think any kind of chemical feed strategy for phosphorus needs to incorporate some kind of algae mitigation strategy. And on the one hand, you could say this is the case for multiple feed points, because if you're able to settle some phosphorus out ahead of the downstream, ahead of the last lagoons where you tend to grow more phosphorus, then you provide less food for the phosphorus to grow, less fertilizer for it to grow, which is true. On the other hand, you settle more solids there, which is not great. And so the other approach is to look at it and say, okay, well, what can we do to manage algae? Well, we can use some kind of chemical to manage the algae, like a copper sulfate type of, or chelated copper product, which I'm going to do a whole presentation on algae coming up here in the spring. I have some on the university site if you want to learn more about how to manage algae. The other approach I would say that we're leaning towards is to actually just cover the final polishing lagoon where we're going to feed the chemical in order to reduce the phosphorus. And by covering it, we actually eliminate the algae or kill a lot of the algae because obviously we're starving it for the sunlight that it needs to grow. So really big, important aspect of this, I'd say, from a foolproof standpoint, you can do your own testing, but covering the lagoon could be a good algae mitigation strategy. Finally, you figured out your chemical, you figured out where you're going to feed it. I think monitoring is key, and dialing in your chemical dosing strategy is going to be important, right? So we highly recommend that you either get an analyzer like this, or you can get a handheld analyzer from Hawk that will literally test the orthophosphate that you've got in the water, the soluble reactive form of phosphorus. And then you can, if you do that testing, and then you also take some lab samples, so you can create a correlation between it at this point in my lagoon, after lagoon 2, my orthophosphate is X and my TP is typically Y. I can kind of draw a correlation, right? And I can say, if my orthophosphate is 2, I know my TP is going to be 3. Then you can dial in your chemical dosing. And by being able to dial in your chemical dosing, not only are you going to ensure that you're going to hit your limit, but you're also going to make sure you're not wasting chemical, right? And the third thing is you're not going to settle too many solids, so that you'll eventually have to remove later. So I highly recommend that you do this monitoring and control piece of the overall project, because that's going to help you to be more efficient, more cost efficient, and deliver a better result. So of course, the downside to the chemical precipitation is you're going to accumulate sludge in the lagoon. You know, the chemical itself is somewhat indiscriminate in terms of its binding to solids relative to phosphorus, and so, you know, the more chemical you use, the more you're gonna accumulate, and eventually those solids have to be removed. The tricky part to that is that, you know, those solids now have a high concentration of iron salts in them, and so in as far as they do, they become harder to remove, and they become harder to get rid of. Not harder to remove, but more harder to get rid of and dispose of, because a lot of landfills don't want to take something really high in aluminum or iron salts, right? So that's something that can be an issue. And the factors that affect this accumulation rate are the level of TSS, level of phosphorus, the level of algae that you've got, the chemical type that you're using, the dosing rate, all of these things. If you wanted to kind of figure out back of the envelope, like how many solids you'd be settling every year, this is kind of a quick and dirty calc, right? Let's say if you have TSS of 30 milligrams per liter at your chemical feed point, you can get 75% removal that you've seen in your jar testing, right, of solids. You know, that means you're going to be left with about 22.5 milligrams per liter of solids that are going to be settled, right? 0.1 mgd, do the calculation, right? So 0.1 times the number of pounds per gallon of water, 8.36 times the milligrams per liter gives you 18.8 pounds a day. All right, so that's what you can kind of expect to accumulate. The reality is that the chemical also has solids in it. So like rule of thumb, if you want to be really quick and dirty, if you have 30 milligrams per liter at your feed point, chances are you're going to settle 30 milligrams per liter, because you're settling both the TSS that's in the lagoon and the solids that are actually bound up in the chemical itself. So this can kind of give you a general sense of how many solids, and you can do that cool thing and put it on a graph and project it forward, and see how long it's going to take you before you got to remove sludge. So a couple case studies here that I want to talk about. This one, like I said, in Michigan, we've been doing total phosphorus projects probably for 10 plus years. And in this particular site, we actually used our injector unit, where we fed the chemical down to our aerator that then has an injector quill in the center of it, releases the chemical, mixes it, and then helps it to settle down. And so we have 8 units, I think, or 7 units in here, or 8 Aries unit injector quills in here on this particular site. So this kind of shows you here the picture of the Aries with the injector quill in it right here. These chemical feed lines come up here to the pump. They're connected to the pump. And the pump obviously pumps it down, connected to the air line, going right down to the bottom of the unit. So from what we've seen from a data perspective, from some of these sites in Michigan that we worked on, is that we're able to easily see that under 1 milligram per liter of total phosphorus. And in this case, Quincy here, we've got, 0.7, 0.6, sometimes down to 0.2, so that's excellent. In Nashville, it's actually way lower than that. It's like 0.45, and so on. So really, really nice levels of phosphorus removal just by precipitating a lagoon. As you can see here, the reason we say 1 milligram per liter for precipitation and not 0.2 milligrams per liter or something like that, as you can see some of the results are here, is just because it tends to bounce around based on seasonality, based on all sorts of things. And so from a reliability standpoint, I think 1's a good kind of target. So the benefit is it's a really simple approach. It's a low cost of implementation. You're talking about a chemical tote, some chem feed pump, maybe a handheld instrumentation, maybe a bi-Aries injector, or maybe just feed it a transfer structure, whatever makes the most sense. You're not building a whole new plant, right? Like you're not putting in concrete tanks. You're not doing a lot of stuff that could cost a heck of a lot more money. And you're able to get down to that 1 milligram per liter and really 0.75 milligrams per liter approach. Relatively simple to operate as well. The downsides are you've got the chemical costs, right? 0.75, yeah, like I said, it bounces around. I'd say 0.1's a good one to bet on in terms of design from all the data we've seen. And the other side is it does accelerate that sludge accumulation, and it does make the sludge harder to get rid of, right? Again, this is why we like the back of the plant phosphorus precipitation approach, because you have less solids at the back of the plant, number one. Number two, you concentrate all of your solids in that last lagoon cell that have the high iron salts in them. They're going to be harder to remove, and then all of your solids upstream of that are fine and can be normally land applied without any issues, right? And then you're going to get more effective overall chemical precipitation. So this is why we highly recommend back at the plant. The other approach here is to put a filter in, and this can be in conjunction with precipitating in the lagoon itself. This system here is a system in Missouri where we have our lagoon, aerated lagoon, followed by nitrox, a reactor system, followed by a filtration system there in that white building. Can be really good at helping you meet that low phosphorus limit and low TSS limits. And you would feed a chemical precipitant, right? That binds to a coagulant, right? That coagulates the solids and the phosphorus, forces it through the 10 micron material, the smaller pieces, the non-phosphorus molecules flow through as filtrate. The phosphorus and the solids stay on the other side of the filter media, eventually to get backwashed. That backwash then gets sent back to the lagoon itself. So there's different forms of this. There's upflow sand filters, as you can see here. There's also cloth media filters, whether that's a disc or in this case a drum. So that's something that we are able to get access to. We have a new drum filter system that's made by our partner and sister company Mida that has some ridiculous like 250 installations with countless examples of great phosphorus removal through their filter media. And so we're able to provide this great system that can help you do this if you need a filter. I'd say, the downsides of filters are that, they're going to struggle with algae. The algae is going to squirt through a filter media, maybe not 5 micron as much as 10, but certainly it's harder. And that algae is going to have phosphorus built up in it. You've got this mechanical piece of equipment that you're adding onto the back of the plant, right? That's got all sorts of moving parts that have to be maintained. So not only is there's an equipment cost to that, obviously there's also a maintenance cost to that as well. But if you need it, like if you have that really low limit, you have that 0.05, that 0.1 type of limit for phosphorus, then this is your ticket. This is your answer. It's very small footprint. You can achieve those limits. It's a controlled process. You have control over the variables, the backwashing cycle, the chemical feed, so on and so forth, and it will just kind of work on auto, right? It'll automatically backwash itself over time, right? And so if you need it, it's a great solution. However, it's definitely a mechanical piece of equipment. It's going to increase operational complexity in my experience. I'd say a multivariate approach is generally good, whether that means that you're feeding, chemical at 2 different points along your lagoon system to precipitate phosphorus and limit the growth of algae to help you precipitate phosphorus, or if you're feeding in a polishing cell and then going into a filter, right? And then feeding right before the filter, that's a good solution. So like if you're trying to get to a low limit, then I would say, you know, multiple barriers is really key. So this system here is in Ontario. It looks super complicated. It's not really that complicated. They just got a lot of valves and bypasses and stuff, but you know, they're running it through Lagoon 1, Lagoon 2, Lagoon 3, Lagoon 4, this covered polishing aeration cell here, right? That's where we're going to inject the chemical. It's going to go from there into our reactor system, ultimately to another flocculation system through the filters and ultimately out. And so this is, they're actually targeting here a 0.07 phosphorus, which seems crazy to me. I mean, it's not crazy. It's going to be done, but like from a low phosphorus standpoint, if you'd have told me we could do that 10 years ago, I wouldn't have thought so. But we've made so many advances in filter materials and the way we approach this that now we can. So just to summarize, you know, it can be difficult to remove phosphorus with water lagoons, particularly when it comes to algae, but you can precipitate or you can filter it out or both, right? A combination of the two. You can really achieve within a lagoon, just precipitating it alone will help you achieve kind of a 0.75 type of phosphorus, total phosphorus effluent, but it's gonna contribute to sludge buildup. If you want a 0.1 or less, then you need a filter system in conjunction potentially with chemical precipitation in the lagoon. But you do need really good algae. You need proper algae control. I mean, it doesn't have to be awesome algae control, but if you don't take care of the algae, that will cause you to potentially not accomplish your TP limits because algae won't bind to the chemical very easily and it will squirt through a filter media itself. And that has phosphorus built up in its cell wall. So that's where I, again, talk about covering your last lagoon in order to kind of knock out a lot of that algae right there. Proper testing on the front end will determine how much chemical you need and what kind of chemical to use. And I think that's critical to success. And then if you need to, you can use a multi-barrier approach. So with that, I open up to questions.
All right, Patrick, I have one for you. Will pond dye work like it does with algae at covering a lagoon surface?
So yeah, pond dyes can be effective. A couple things about pond dyes. One is that pond dye is less effective at killing algae that already exists than it is at preventing algae from existing in the first place, right? So it doesn't attack the algae, it just attacks the sunlight's ability to help the algae photosynthesize and thrive. So it's a proactive, a better proactive than reactive approach to algae. The second thing is, obviously, as you get water running through the lagoon system itself, it's diluted. And so you have to constantly add more pond dye, right, over time. You got to stay on top of it over the summer months in order to try and prevent the algae from growing. I would say from a labor and just a cost of material standpoint, you know, there is a point at which the amount of time and cost to you to putting the pond dye in, and you've got to spread it around the lagoon, you got to make sure it gets good coverage, all that stuff over the course of the summer and really being on top of it versus, let's say, covering a final lagoon where it's a set it and forget it type of approach. You have to start to look at where that cost benefit factors and where the break even is. I understand covers can cost money because you have a lot of square footage out there, but you only need to really cover 3 to 5 days of retention. You don't have to cover the whole entire lagoon in order to get effective algae reduction out of that. So that's kind of where I sit on it. I'm kind of like, for me or my money, I put the cover out there and forget about it, right? Because it's just going to work versus I got to dye, I got to make sure I get on it early enough in the spring, I got to stay on it all summer long, etc. So you may also with dye, you may end up having to use copper sulfate anyway, because if you don't stay on top of it or you get busy or there's big rain events or something like that happens, it's hard to really be on it from a pond eye standpoint.
Follow-up question, what do you recommend for covers?
I'd say like those hexagons that I show in that picture are a good solution, or the bird balls. Bird balls don't get theoretically quite as much coverage, but it's like it's a difference in 5% maybe. It's not going to make a huge difference to the overall algae growth, but both of those are really easy to install. They're relatively inexpensive for covers. They're probably the least expensive option, I would say, for covers, and they'll get the job done.
In a system where you might have to remove multiple nutrients like ammonia and phosphorus, what is the order of these processes? And does one process interfere with another?
So there doesn't have to be a particular order. In theory, yes, you need like 0.02 milligrams per liter of phosphorus in order to grow the nitrifiers that you need, but it's such a small amount that it's almost impossible, I think, to starve the nitrifiers of all the phosphorus they need to thrive. So you could do it before or after. I think just logically, it makes sense to me to do phosphorus precipitation after ammonia removal, partly because what we've seen with our reactors that are after the lagoon at the end of the process, right? We see breakdown of BOD in those reactors, and we either see a reduction in TSS or in some cases we see a slight increase in TSS. And to use the precipitant to both take out the phosphorus right at that point and the solids at that point after the reactor seems to make a little bit more logical sense.
Duckweed, if you add it, needs to be harvested, correct? If so, should it be in the last pond or the first pond of a system?
So last pond. That can be a nice natural cover versus the bird balls approach, or the hexagon approach, and I've seen that. The downside to it is that wind will blow duckweed around, right? So it doesn't always universally cover the basin if that you might want. However, so when it comes to harvesting, yes, it is important to harvest it, because what it does is that duckweed will ultimately assimilate the phosphorus into its cell wall. It'll grow, thrive over the summer months, die in the winter months. That duckweed will sink to the bottom and be part of the sludge blanket. On one hand, you're like, great, it's part of the sludge. I love that. That's exactly what I want. On the other hand, because it's not bound up with chemical precipitant, or if it's not bound up with chemical precipitant, is that it actually will break down anaerobically on the bottom, and it can re-release that phosphorus into the water column at some point in the summer months, which can actually lead you to having a spike in phosphorus. So if you do have duckweed, to harvest it is good, because when you're managing it, when you harvest the duckweed, you're removing the nutrients at the same time, right? And so you're not going to get that compounding buildup of phosphorus that could potentially lurk underneath the surface and rebound at some point.
What types of plants are used in constructed wetlands?
I don't know. Sorry. I don't know the answer to that question.
We'll get back to you on that one. I'd like to share this comment, which seems very educational, and you can comment on it afterward. You already have an anoxic zone at the beginning of your basin for the recycled NO3. If you can create a slowly mixed zone at the beginning with built-up sludge, you can create a septic zone for creating the required VFAs and PAOs. Once these are created, you just need to go aerobic for PAO uptake and keep it aerobic so the P does not go back into the solution. Then you need to remove the sludge, perhaps from a location where you can concentrate it. If you dewater remove sludge, the liquid portion is sometimes returned to the treatment process. However, that liquid could be high in phosphorus. It may be possible to land apply dewatered sludge and separately irrigate the liquid portion to keep all removed P out of the lagoon.
Sounds cool. Give me a call. We can give it a shot. I'd love to learn more.
Any experience with PO4 or phosphate removal on cold climate constructed wetlands? And side note, are there cold climate constructed wetlands?
Part one of that question is no. Part two is yes, I believe there are some cold climate constructed wetlands. So our VP of Sales and Marketing, Patrick Engel, lives in Wisconsin, has done a lot of lagoon work in Wisconsin, and said that where they have very low phosphorus limits, and said that there were some lagoons that put in constructed wetlands to accomplish the low phosphorus requirements that Wisconsin has, and that he's, the sort of anecdotal and, very unscientific and undata backed comment was, this works well for 2-3 years, and then eventually the plants in the constructed wetland died and started to break down anaerobically and re-release the phosphorus back into the water, which then ended up basically burping phosphorus into their effluent. So that's what I know. I think logically, obviously plants are going to grow less in the wintertime, and so in a cold climate, it seems like constructed wetland doesn't make a lot of sense. However, I guess if you size it correctly or if you use a certain type of plant, maybe it does. But again, not an expert on constructed wetlands, so not sure.
Is there a recommended method of keeping duckweed out of a discharge? And have you heard of any states passing laws saying that discharging duckweed is equal to discharging the ammonia and phosphorus it takes up?
No, I don't think there's any law there. I think the way to not discharge duckweed is to pull your effluent for the lagoon underneath the surface, like 2 feet below the surface, right? So duckweed floats, and so if you have your effluent pipe, 2 feet below where the duckweed's floating, you shouldn't suck any duckweed into it. Largely speaking, you shouldn't. And I've seen that a bunch. We actually really like lagoons that are covered with duckweed at the final lagoon. We have a system in Missouri that has it, and I always love going to the effluent and looking at it because it's just like crystal clear. Like it's just turns into this beautiful wastewater because there's no algae in it. It's quiescent lagoon at the back. They have a ton of duckweed on the lagoon, and there's, just looks great.
What are you seeing for trends in permits? Do facilities that have ammonia generally also have a phosphorus limit?
No, not right now. It's usually one or the other, unless you're in a particular watershed where they really want you to have phosphorus. And it sort of seems random, right? So it's either you get a phosphorus requirement or you get an ammonia requirement. So like Michigan, for example, they've got phosphorus requirements. They don't really have ammonia requirements yet. They're talking about it, but they don't have it yet. Missouri, on the other hand, doesn't have really any phosphorus requirements, but has ammonia requirements, right? And it's generalizing here. So there's definitely lagoons in Michigan that I'm aware of. Silver Dollar City, for example, is a lagoon in Missouri that has a phosphorus limit, right? But that's because it feeds into a watershed that goes to a lake that is sensitive, as a sensitive ecosystem. So, but in general, so usually it's one or the other. But I think the sort of trend that I see, and talking to regulators, if I talk to them and say, where are we going here? A lot of times they're saying like, yeah, well, we started with ammonia and we're probably going to go to total nitrogen, or we started with ammonia, we're probably going to add phosphorus here. We're going to start monitoring phosphorus in 2 years, and then 5 years we're going to put phosphorus in the permit, right? So I think it's just a gradual build, and what order they go from, whether it's ammonia, phosphorus, total nitrogen, or ammonia, total nitrogen, phosphorus, or whatever, it depends on the state and how they want to approach it. But in general, I think the 10-1 is the rule of thumb. You're going to get a 10 total nitrogen, you're going to get a 1 phosphorus at some point.
Are you seeing many TMDLs where it's just the bucket of nutrients versus separating them out?
No, I haven't seen any.
Any opinion on feeding polymers like neowater instead of ferric or alum?
Nope. I think there's a number of ways to skin that cat. And I think it all comes back to doing your own testing, doing the jar testing, seeing what best works for your lagoon.
That is our last question.
Excellent. Thank you very much. Eve's going to email about CUs and PDHs, so take a look for those. Look forward to potentially seeing you back in the spring when we continue our webinar series, and best of luck and Happy New Year. Merry Christmas.